Okay, so let's spend a couple minutes talking about the project. So here's the project. I think I gave you a little taste of what it was going to be about later, or when we first started. But here's the deal. This is going to be a project called the physics of something, or the chemistry of something, or the earth science of something, or the astronomy of something. In other words, all I want you to do is do a little bit of research into some topic that we've either covered or not. I don't really care if we've covered it, as long as it fits within that category. And that's a very, very, very broad category, right? If you can relate it to physics or chemistry or earth science or astronomy, it's fair game for this project, okay? You can either do one of two things. You can either do a 600 to 800 word double-spaced paper on this, which is really only a couple pages, I think. Or you can do a 5 to 10 minute presentation on it, which you just stand up here and you talk about it. And you could have slides if you want, or you could have a handout or some visual aid. You have to have some visual aid altogether, whether you're handing a paper or not. You've got to have some visual aid that you create somehow. Now, I know that this is not the best area of the world to be in to try to get visual aid making materials, but do the best you can. And if you have trouble with that, let me know. But what that doesn't mean is like take a picture from the internet and put it in your paper. That doesn't count. You can do that to an extent, but you also need to create some visual aid that you personally like have drawn or created or whatever.
Can you do a combo?
Can you do a combo of a paper and a
300 words and
3 minutes?
5 minutes.
Sure, if you want to do a combo, fine with me. Yep. What we'll probably do is whoever's going to do the little presentations, we'll just take however long that takes during one of the lab periods or maybe one of the class periods, whatever, and we'll do that. Just tell me, I'll ask you to tell me which one you're going to do, say, in like a week and a half. Because you've got 2 weeks to do this. Okay, it's not due until the 29th of April, which is 2 weeks from today. Okay, and it's going to count as part of your project grade, which I'm gonna adjust the grading scheme in the that we talked about in the syllabus, just because we haven't exactly followed it, and we did talk about having homeworks and having projects, but we're going to adjust it. Again, my goal is not to fail anyone in here, so even though I would like you to do better on the tests, for those who didn't do so well, my goal is not to fail you. You may not get an A, but you should do all right, especially if you try hard to do on the project. Okay, any questions on this so far? You want an example? Let's say I wanted to do the physics of an air conditioner. Okay, I might say, okay, well look, an air conditioner. I look this up and I go, how does an air conditioner work? And I go to like howstuffworks.com and it tells me all about air conditioners, how that works. And that could be one of my sources, right? You can use an internet source because there's not exactly many books here on base. I mean, there are some, but you'll probably not find the ones you want to use. You can use the source, and you go there and it says, hey, an air conditioner uses some gas that it actually expands, and when it expands, it cools, and then you pass air across it, and it condenses, et cetera, et cetera. And there's a motor in there that's got to condense. And anyway, you talk about that in your paper. Now, you can't copy word for word, right? That's called what? Plagiarism, right? You guys all know that. Don't do that. And it's so easy to check these days, especially if your source is an online source. Like I do the same Google search as you guys do, right? So it's so easy to check. You got to make it your own. You got to make it your own words. Okay? Anybody unclear on that? If you have an example of you're like, well, I think I used my own words, send it to me before it's due, and then I'll look at it and see if I can find it on Google or whatever myself, right? So you can't really use the same sentences and so forth. You got to describe it in your own words. Okay. So anyway, so I do this project. I decide that I'm going to do a little presentation on it. And so what I do is I take the air conditioner out of my room, and probably don't do that. Maybe if there happens to be an air conditioner you want, we can do that. But I might draw a little picture of the various parts of an air conditioner or something like that. And you can do it on a computer program, or you can do it by hand, and I can Xerox things for you and whatever. And then so I might have a little kind of a overview of the air conditioning cycle, blah blah blah, right? And then I talk about it for 5 minutes and I'm done. and I hand in a little thing that has bibliography, and that's it. Okay, if I do a paper, I'd write the paper up and describe it as well, have my visual aid somehow included in my paper or attached to it or whatever. Okay? Question?
Well, if you do a paper,
Mm-hmm.
so you don't have to use,
You don't have to sit up here and talk, no. But maybe we might do one more short project where I might make you talk if you didn't. Just because, you know, should have, but I might not. We'll see. Probably don't have time. Probably don't have time.
Does it have to be like a poster or anything for, like,
No,
visual
it can be. You can be creative. However you are creative. If you want to come up and say, you know, we've got a hot plate. If you want to show boiling and you want to say, hey, look, this is a cooling process, and you can show how, you know, whatever, something like that, or evaporation of some. If you somehow figure it out and you want to use something real as your visual aid, great, perfect. Okay. All right. So it can be anything we've studied in class. You can look through your book for stuff we haven't gotten to yet. You can look for stuff online, whatever. But you got to just kind of relate it back. Try not to make it too biology heavy, because this class isn't about the biology end of things. Okay. So I mean, if you want to talk about artificial limbs or something and the mechanics of those, that's fine. But you know, you don't really want to talk about how the heart works. No, that's biology, not physics or chemistry. Okay. Now, if you want to talk about how electricity is used to regulate the heartbeat, that might be different, right? Because that's a physics term. You have to talk about, you know, the type, that sort of thing. You can, as long as you relate it back. But again, this isn't a biology project. It's a physical science project. Okay. All right. Good. And I won't assign you much homework aside from this. I suggest not starting it next Sunday or 2 Sundays from yesterday, because you probably won't have a good time with it. Okay. Let's see. Anything else? Did anybody look over their test and find other mistakes on their tests, of grading mistakes? No? All right. You feel free to do that. If you find a mistake, points. Yeah.
The test review online is still valid, or?
The test review is still valid. Yeah. It should be. If you can't get to it for some reason, then let me know. It should still be okay. Yeah. Okay. So tonight we're going to talk about mixtures and chemical reactions. Now, the nice thing is we actually did a whole bunch on mixtures last night with moles and molarity and all that, so we can kind of breeze right through this. Okay, I'll show you at least 1 or 2 little short videos. Just to show you that this guy that does the second part is not not my favorite lecturer in the world. I'll show you a little clip from him. Sorry? This is chapters 16 and 17. Believe it or not, we've gotten all the way to 16 and 17. Yeah. I know you missed 1 day, you missed 2 chapters. Boom. Just like that. Yeah. We're flying. Okay, but hopefully, we're halfway through, right? So hopefully you guys are getting a feel for, like, you know, the class and the kind of the topics. So again, I'm not trying to make you into experts. And I'm not even an expert on a lot of this stuff, so. Okay, so mixtures and how chemical reacts. Let me start out with a couple questions. And this was straight from your book. How do you separate fresh water from seawater? Can a fish drown underwater?
Yes.
Where do sugar crystals go when you dissolve them in water? What happens to them? And we can answer all these questions, if my computer doesn't die. There we go. We can answer all these questions when we talk about mixtures. Okay? How do you separate fresh water from seawater? Seawater is actually a mixture. Okay? It's not like, there's not elemental like changes to the water. It's a mixture. Fish drown in water. Well, fish actually breathe what?
Oxygen.
They breathe oxygen, right? So if there's not oxygen in the water, well, we'll find out. So oxygen in the water is actually a mixture. And where do sugar crystals go when you dissolve them? Well, we gotta figure out where they go. Right? They don't just disappear or somehow, you know, get into some weird state. Okay. So a mixture is just a combination, 2 or more substances, in which each substance retains its own chemical properties. Now, that's not necessarily the properties that it had when it was like a solid, because we saw salt. When salt dissolves, right, the ions do come apart, right? And it actually, those ions are still in this like liquid state. But it's not part of the water. Like, it doesn't like somehow change the water itself. It changes, it's just a mixture, meaning there's salt in the water, and they're chemically reacting, but not in the sense of changing the types of atoms that we're talking about, or the types of molecules we're talking about. Okay. The other day, I think it was Tom who said, hey, what about alloys? Are they mixtures, or are they something else? Alloys are mixtures. So stainless steel is a mixture of iron, chromium, nickel, and carbon. Okay, and stainless steel is pretty hard metal that doesn't rust, right? Well, it's not supposed to anyway, right? Well, what's that? Your ring is stainless steel? There you go. Excuse me. Seltzer water. So we can have mixtures that are actually metals. We can have mixture or solids. We can have mixtures, of course, that are liquids. Water and carbon dioxide. It's actually kind of a mix, right, of a liquid and a gas in mixture. And then our atmosphere: nitrogen, oxygen, argon, carbon dioxide, water vapor, a mixture of all that stuff. Okay? All right. We can separate mixtures. It's not necessarily easy, but we can separate mixtures using physical means. We don't have to use chemical formulas to to separate mixtures. Okay? This is a distillation setup. What you've got is you've got water here, let's say like salt water, okay, and you boil it, and as the water molecules turn into a gas, they go up here, and then you can actually cool this pipe down a little, and they will condense down here and then drip down here into here. The salt does not go out of here, so you end up with fresh water. It's not going to be perfectly fresh. It's going to be close. You can't get perfectly fresh water. There's always going to be some impurities. We'll get to that in a little bit. But for the most part, this is how you'd get one way to get fresh water. We'll talk about another one right at the end of class. Let's say we had a solid and a liquid mixture. You might be able to use a filter to do it, right? When you mix your, anybody use a French press to make coffee? What you do is you dump coffee grounds into water and then stir it around. Now it's a mixture of those coffee grounds and water. And then you take a filter and you go whoosh, and you press it through, and all the coffee grounds go to the bottom, and what's left is the coffee, which has the caffeine and has the taste and all that in it. Okay, but you can do that with a filter. You can also do it when you use the actual paper filters too. Same sort of thing. Okay, and if you have things at different boiling points, do you remember what salt boils at? Anybody remember? What it melts at, rather? Not boils. Melts it. Actually, it's even more than that. I think it's like 800 degrees Celsius. Yeah, salt is you're gonna have to really crank the temperature up to melt that salt. Okay, and it has to do with the fact that the bonds are so strong in saline, in salt. So here's a little chart that talks about the different types of mixtures. Okay, you've got, well, types of matter, I should say. You've got pure matter, which is all the elements we were talking about. Okay, and also the compounds like salt. Okay, so NaCl is not a mixture, it's an actual compound. It's a molecule. You've got those bonds coming together and actually linking, and now it's a compound. Carbon dioxide, pneumonia, nitrogen, sulfur, all those things are elements or compounds, and they are what we call pure. Again, you're never going to get it totally pure. Does anybody know what we try to make the most pure in the world, the substance we try to make the most pure in the world? Not gold, although we try to make gold pretty pure. Not some diamond, I don't think so.
Coal?
Not coal. Coal's pretty impure, actually. Fossil fuels, no. You use it every day in your computer, your iPhone, your television. Yeah, there you go, silicon. You know, computer chips are made out of silicon, right? And the way they do it, it's kind of a complicated process, but they take silicon and they make it as pure as possible. And then they start adding impurities, but that's what makes the transistors in it. So the less impurities you have, the smaller your microchips you can make. And we always try to make things small and the more efficient, and they work better. So it's all about being able to make a high number of microchips, because it's really expensive, by the way. To make a design of a microchip, number one, takes engineers years, and then it takes a lot of really, really, really pricey stuff to make those microchips. So you want to get the cost per microchip as small as you can. So you make it more pure, make the silicon more pure, and all that. So anyway, those are compounds. Now we've got mixtures. We've got two types of mixtures. We've got homogeneous mixtures, which are mixtures where you can't look at them and tell that they are a mixture of something. Okay? You've also got heterogeneous mixtures, which is where you can tell. So let's say you pour sand into water. Now we know sand doesn't dissolve in water, right? That'd be a little weird, because then the beach, it would be dissolved, it washes up. That's weird, right? But sand in water, you can tell. You can look and you go, okay, there's sand, and I see the water around it, and whatever. Oil in water, We know that doesn't mix together, right? We'll talk about why that's the case. They actually separate. Okay? Sand and salt, if you mix sand and salt together, you can see the sand and see the salt, as long as it's not, really white sand or something. You can still tell, though, that it's not a mixture that's the same throughout. Homogeneous mixtures, I think, are some cases the more interesting ones. Air. Well, first of all, you can't see air because it's transparent. But if you were to look at it, you'd still say it's just gases. And those gases it looks the same. Like all of the individual pieces, sure, there's different molecules in there, but it's homogeneous in that it's all mixed together, the same amount. Okay, salt water, white gold. Anybody have any like white gold? It's kind of cool looking, if you ask me. It looks kind of like silver, but it's part gold, part palladium. It's different.
Does it look like platinum?
It does look a little like platinum, yeah. Yeah, it's very shiny, very white, yeah. Or kind of silvery, I guess. Okay, so those are the types of mixture, types of matter, and the types of mixtures in particular. Homogeneous and heterogeneous mixtures, okay? All right. Okay, I mentioned this a little earlier. Pure is actually a very relative term. Okay, pure, we say something's pure. Well, we're really never going to get it 100% pure. Even that silicon that we have, you can't make it. Remember how small atoms are. They're so tiny that you're never going to get rid of all of them. You can make something 99.999% pure, right? If you keep purifying it, generally it's expensive to do something like that. But we can just talk about the different relative purities. Okay? All right, kind of already mentioned this. Homogeneous mixtures, different compounds seen as individual components. Heterogeneous. So like another example of heterogeneous mixtures, the pulp in orange juice. Like pulp's in the orange juice, but you can tell. Like you look and go, there's the pulp and there's the pulp. You can't do that with regular mixtures, or with homogeneous mixtures. Okay? Solution or suspension. By the way, milk is a mixture, right? Because the fats in milk are actually not really dissolved in the milk. It is a homogeneous mixture because you can't tell. You look at milk and you go, okay, I can't see the fat particles, but they're in there. Okay? And if you ever tried to filter milk, yeah, you get like the fat sitting on the top, and you get some other stuff. And when you boil it, you get the fat particles as well. Yep, good. Okay, in a solution, everything's in the same phase too. Okay, they're either liquid phase or gas phase or whatever. And as I said, milk and blood and clouds are this suspension, which is different components in different phases. Okay, like in milk, you've got the liquid milk, the liquid watery part of the milk, and you've also got the fat, which is solid, but they're mixed together. Okay.
So seltzer water would be a heterogeneous mixture?
Seltzer water is seltzer water is actually homogeneous because it is. I think I said that they were all in the gas. It's actually in when it's mixed in and not coming out of solution, then it's all liquid.
Okay.
Yeah, but once you see the bubbles, that's not really in the solution anymore. It's kind of traveling through the water at that point. Yeah. Okay. So if you mix sugar into water, okay, what actually happens? Okay, take a look at this picture. These little guys are sucrose, I should say big guys, are sucrose molecules. Sucrose is I have the formula here somewhere. I forget if it's on the next one. No. Sucrose is a relatively large molecule. Okay, salt's relatively large. Or sugar rather, relatively large. When you dissolve it in water, the tiny little water molecules are there. They pull apart the sugar from the other sugar molecules, but they don't pull apart each individual atom. Unlike when you dissolve salt in water, you end up with the sodium and the chlorine ions coming apart from each other and going everywhere. In this case, the sugar molecules stay as sugar molecules. Okay? All right, so what happened? Oh, there we go. Okay, and it stays in its crystalline form. I'm sorry, it loses the crystalline form, but it stays, its bonds stay together. Okay, so now I want to show you this video. I may have it on my computer. Let's see. This is by the other guy that wrote the book. I just thought I'd show it to you. Let's see. Mastering Physics, chapter, it is 16. No, I didn't even download it. Let me do it from over here. Okay.
Years now.
Louis, did you get my email yesterday? Did you get my email?
Yes, I did. I sure did.
Good. You should have said no if you didn't want to do it.
No, I'm honest. I'm honest.
Oh, all right, good.
I joke, but I'm honest. Genuine.
I know you are. Okay, let's see.
But I'm also a pro.
I see. You are not a corpsman, and I know it.
I'm like a corner, but not really.
But not really.
If you don't think about it, it makes sense.
I'm not going to think about that, because I don't know what that means. 16 mixture. Oops. No, you know what? Okay. You guys who have access to the website, you guys know you can go to the book online, right? And you can read the whole book, and they've got these little cool videos there. If I click on e-text, that should go there.
Videos in a loose form, right, sir?
Well, the other videos are cool. I like the Hewitt ones. This guy, I don't know. I'm a little. I feel bad. He might watch this tape someday. He's a nice, real nice guy, but I'm not thrilled with his teaching style.
That kid that we were watching the video yesterday from, the guy who was teaching us.
That guy was good, wasn't he?
Yeah,
That guy was pretty good. I don't know who. Did you call him a kid? I think he was a teacher. I don't know. He didn't look that old. That's true. Let's see. Okay. Let's see. Solutions. Is that where we are yet?
Definitely at the moment.
What you call yourself?
Here we go. Okay. I think this is the one.
Baby. A baby.
Yep. This is it.
Look at what we have here. We've got some sugar.
Oops.
We have this cylinder filled with water. How much water?
Sure. You can hit the lights.
Exaggerated?
450 milliliters of mixture. And we have this beaker. Check this out. The beaker is bone dry. How about we do this? Let's take the water and put it into the beaker. The 450 milliliters of water.
Now we know how to pour as of yesterday's lab, right? I think he wouldn't do very well pouring like that.
And I'm not going to spill a drop outside of that beaker. It's all collected in the beaker. How much volume of water do we have in here? 450.0 milliliters. And let's take the sugar and add it now to this tall cylinder.
This is regular sugar.
What would happen if I added the water back to the cylinder? Well, if this is sugar, the sugar is going to dissolve. And fill it up just a little way so I can pick it up and shake it.
I think that's a cool piece of glass, though, isn't it? It's like got a little bulb down here and another bulb up there, and it's like a hookah. It does look a little like that.
Add some more water.
Yeah.
If you look carefully, you can see how it is the sugar has dissolved in the water.
Is that thing specifically so that you can stir it like this?
So
Maybe,
that it's
I don't know.
transparent.
I don't know. It's a good question.
I'm going to add the water back to the cylinder. And I'm going to add all the water back to the cylinder. And I got a question for you.
Crazy talk.
It's crazy talk.
After I add all this water back into the cylinder, will the water level stay below the original level? Will it come back up to the original level? Or will the water rise above the original level? 450 milliliters.
What do you think? I know. I know. It's a little too dramatic, if you ask me.
Sugar. Because sugar weighs more than water.
It's not because sugar weighs more.
The volume is now greater than 450 milliliters. Why?
He's trying to be
You're
like
not confusing this with an earlier demo that you saw, are you? You know, where we took 50 milliliters of water and 50 milliliters of ethanol, we combined them together and came up with 98 milliliters of mixture? There we saw that the volumes weren't quite additive. They didn't add up all the way to 100 milliliters. But
That's an
they
interesting
did
one.
add up to some value, 98, which is greater than 50 and greater than 50. Here we had 450 milliliters of water. And we also had sugar. Does sugar occupy volume? You bet. The sugar occupies volume, whether it's in the water or out of the water. So as we added the sugar to the flask, and then we added the water, and we stirred it up, what happened to the sugar? The sugar lost its crystalline structure. In the crystalline form, you have sugar molecules packed together neatly like this. And then, when the sugar dissolves in the water, you lose that structure. The sugar molecules become dissolved in the water, but they're still there in the water. If I were to taste this water, it would be a little bit sweet. Why? Because of the sugar that's in there. The sugar continues to occupy volume, whether it's in the water or out of the water. And we can see that it occupies that volume. When you have the water and the sugar combined, the volume is greater. Make sense? You bet. We're seeing a material dissolve in another material. And the two materials continue to exist. They exist in a state where they are blended together. And don't forget that when a solute dissolves in a solvent, the solute still continues to occupy space.
Guess that's it. All right.
Back to the basement for you.
All right. So, yeah. So in this case, his point was, well, a little bit too drawn out, if you ask me. But the point was that obviously sugar in a solution has volume. He mentions this other little experiment, which is pretty cool, actually. If you take, well, he said it, but if you take 50, it's like if you take a bottle. Let's say you take half a bottle of water and then half a bottle of ethanol, which is a kind of alcohol, and you pour them together, you actually end up with less than a full bottle, which is a little weird. But it's because they actually combine together, and you end up with a solution where the molecules are actually closer together than before. Like, so everything packs in a little bit closer. So you can get a decrease in volume by adding two of the same amounts together. Kind of cool. Yeah. Is that you?
Turned that silent, so I guess I figured that out inside the text.
Oh, all right. All right. So the sugar solution. Could you tell where the sugar, if it was in a state where it wasn't saturated and you kept adding sugar, you could tell the crystals were on the bottom like we did yesterday, right? But if it wasn't saturated yet, could you tell that the solution where the sugar started and the water stopped from looking at it? Well, if it wasn't saturated, if you stirred it perfectly, you wouldn't be able to tell. And that means it's a homogeneous solution. And basically that means that if you take a sip and it's sweet, the first sip will be the same sweetness as the last sip. Now that never happens for me with like iced tea or whatever because I never stirred enough, I'm sure, but oh well. All right. So again, solutions don't have to be liquid. Okay, rubies, you actually have red chromium and aluminum oxide, and they're mixed together, and you get that really cool look of rubies, kind of shiny, and so you can see through it a little bit. All right, alloys, we already mentioned this before. Brass, mixture of copper and zinc, bronze, copper, and tin. So if you're in the Olympics and you get a bronze medal, it's not an element like the gold or the silver is. It's actually copper and tin.
How about the tin metal?
The tin metal, that's if you get caught drugging yourself. That's a tin metal. You can also have gaseous mixtures, of course. Air, which is oxygen, nitrogen, carbon dioxide, argon. Anybody know the relative amounts of these? How much? Question. Oxygen, nitrogen, carbon dioxide, or argon. Which one has the most percentage? What do you think?
Argon.
Argon? Okay. There's one argon. How many people think oxygen has the most percentage in air? The air you're breathing, the most of it is oxygen. Raise your hand. Nobody? Okay. How about nitrogen? 1, 2, 3, 4. Okay. How about carbon dioxide? 1, 2, couple, 3. And how about argon? You going with argon? Argon's like 1% or less than 1%, so not quite. But there's more. It is the fourth, I think, right? Not argon. Carbon dioxide. If carbon dioxide was the most, we'd all die, right? That would probably be bad. You'd think if nitrogen was the most, we'd all die, but that one actually is. Anyone know what percentage it roughly is? I think it's 78% of the air we breathe is oxygen. Nitrogen. 78% is nitrogen, right? Which leaves about what? Well, I didn't say the other percentages, but I think oxygen's like less. It's obvious less than 20% oxygen in the air we breathe. So if you ever see like like the football games and the guys are like sucking on oxygen, that's actually more pure oxygen. It's probably not 100% oxygen, but it's more pure oxygen. They give it to people who are like infirm or whatever. They'll give them those little oxygen tanks, and that's more of a higher percentage because as you get older, excuse me, if you are working out, you might be able to use more oxygen. It's not good to breathe 100% oxygen because you will actually poison yourself with 100% oxygen. So for a long amount of time anyway. Okay. What else was I going to say about that? Oh, if you're a diver. Any other divers in here? Scuba divers? You should do it. It's awesome. But it doesn't matter. Yeah. Okay. Oh, you've done it, but you're not a diver. I see. Scuba diving is cool, but the scuba tank basically has air, compressed air. But if you're going to go deeper, you can actually get tanks that have a higher percentage of air or oxygen, higher percentage of oxygen, so that you can stay down longer and so forth. Still got nitrogen in it. If you're going way deep, like in those research vehicles, some people go into those, you can actually get solutions where it's oxygen mixed with neon, or probably not neon, probably helium actually. Yeah, it's mixed with helium, which makes your voice sound funny while you're down there, but it's just the right amount of oxygen. And they do it so that, why? What's wrong when you dive? What happens when you dive?
Immense pressure.
Well, what do we have to worry about when we're underwater? Which of these? Nitrogen. Yeah, the nitrogen in your bloodstream is only so soluble in your bloodstream, and the higher pressure you're under, the less soluble it is actually. Okay, well, sorry, I lied. The more soluble it is when you're at higher pressure. And if you're breathing in oxygen, more nitrogen will actually go into your bloodstream. But then when you go back up to the surface, the nitrogen is now less soluble, and it comes out of your bloodstream. And when gaseous nitrogen comes out of your bloodstream, it bubbles. And that causes something called the bends. And it can also give you strokes and heart attacks. And it's bad news. Bad news. So anyway, so we try to limit the amount of nitrogen you get. And that's why if you are a diver, you can only stay underwater for a certain amount of time at a certain depth. And the SEALs know all about that. Probably the PJs too. Okay, so we did a lot of this yesterday, right? Solutions, solvent, solute, saturated, unsaturated. Remember all that from the lab? Just real quickly to review, solvent, the compound present in the largest amount, it's what does the dissolving. It's the thing that dissolves the solute, which is what gets dissolved. Remember, saturated is where you can't put any more solute into solution. Unsaturated means you still can put some more in there. You haven't reached that limit yet. The concentration, okay, is the amount of solute divided by the amount of solution. Normally we measure that in what? Moles, not just moles, but moles per liter. The moles, we'll get to what a mole is again from a review from last night in a little bit, but we measure the concentration in the number of molecules, which is the amount of solute, divided by liters. This idea of amount of solution, it normally means the number of molecules, not the mass. If you take a beaker and you have so much water in it, you might have 100 grams of water. And then you put 200 grams of salt or sugar in there. 200 grams of sugar in that 100 grams of water. Well, if you count amount as mass, you're going to say that the sugar is actually the solvent and it's the water that's the solute. But that's not really the way it goes, so we normally do it by the number of molecules. Because water molecules are so much smaller than sugar molecules, there's way more molecules of water than sugar. So we count that as the part that determines which is the solvent and which is the solute. Okay? But anyway, we talked last night, a mole, 6.02 times 10 to the 23rd of anything. You remember how many thousands of billions it is? Well, let's see. So this is the way I always think of it in terms of billions, because I think it's easier that way. A billion is a 1 with 9 zeros after it. Okay? It used to be 12 zeros in Great Britain, but don't get me started. 9 is the standard these days. A billion is a 1 with 9 zeros after it. Okay? A billion would have how many zeros? 18 zeros, right? Because it's got 9, and you take a billion of those, and that adds 9 more zeros. So if we're up to 18, we've got a billion, right? Now, 23 is how many more than 18? 5 more. How many zeros? If you have 5 zeros and a 1, what number is that? 5 zeros. 5 zeros would be 100,000, right? Because let's just write it down. Yeah, it'd be 100,000, right? Because you got 1, 2, 3, 4, 5, right? Put the comma there. That's 100,000, right? Okay, because 6 is a million. So anyway, we have 23, 10 to the 23. That's 100,000 billion. That's how big that number is. Now, really, we can't really think of that, in terms of like an actual size, because it's such a big number. We haven't really gone into detail about scientific notation in here, but scientific notation gets big really fast. Okay, really, really fast. So, for instance, how many protons, electrons, and neutrons do you think there are in the entire universe? 10 to the what? Yeah, a lot. So what's that, a lot? 1,000 million, 10 to the 1,000 million billion? What do you think? A trillion, 10 to the trillion? In the entire universe. Remember, there's billions of galaxies with billions of stars each. So what do you think? 10 to the what? It's actually about 10 to the 76th.
We're way off.
Well, remember I said that 10 powers of 10 get big really, really, really fast. In fact, I'll show you the little, I think it's online, the powers of 10 video. I don't know if you've ever seen it in high school. I'll show it to you in a minute. But 10 to the 76. Let's think about how big this is. We can kind of think this out. Okay. Okay. A mole. We've already said 10 to. Let's start with 10 to the 23rd. Okay. A mole is like a handful. Okay, or less. Let's say a mole of sugar is like a handful of sugar. Okay. It's like 200 grams or something. Okay. So you got it in your hand. You have a mole of sugar. That's 10 to the 23rd. So what's 10 to the 24th? How many hands do I need for 10 to the 24th of sugar? One more hand? That would be 2 times 10 to the 23rd. I would need, how many? We're doing powers of 10. You'd need 10 more hands. OK, so we've got 5 of us here. Now we've got 10 to the 24th. OK, bear with me here. OK, how many? So that's 5 people, right? How many? Let's say each only just one's hand. So it's 10 people. We'll make it easy. 10 people, right? How many people do we need for 10 to the 25th? Not another 10 people. That would be 2 more. No, not another 2. Nope. Another 10 more, meaning another 10 times more, which would be 100 people. So you'd need 100 people to hold 10 to the 25th. let's just keep track here. I'm going to prove to you that this is a huge, huge number. We're up to 25, okay, and we've got 100 people. Okay, 10 to the 26th, right? That's 100 people. Could you cram 100 people in here? Yeah, you could. There's 10 of you. You could cram everybody back in here. You could cram people in, right? So that's like a building. 10 to the 25th is about a building's worth, let's say. Okay, so far so good? Actually, it's probably 10 to 26. We'll probably go 10 to the 27th as a building because really we're only talking a hand. So that's like 100 hands. So now it's times 10, 1,000 hands. So you've got 1,000 handfuls of sugar. You think it might fill this room? Maybe. Let's say it does. 10 to the 27th. OK, 10 to the 28th. What do we need now? 10 what? But let's think about it in terms of the size of this building. How many of these buildings do we need? 10 buildings. And we're now up to 28. OK, 29. Then what do we need? 100 buildings. 10 to the 30th. 1,000 buildings. So that's pretty much the size of like the base here. If you crammed buildings in, there might be 1,000 of them. Right? 1,000 clues this side. These are like double wides, right? So 1,000 of these, right? OK? Well, don't you wish your clue was this big? A huge amount of space. Huge. So 10 to the 30th, we're talking the size of this base. What's 10 to the 31st? 10 bases. What's 10 to the 32nd? 100 bases. 10 to the 33rd, 1,000 bases. Now we're talking about like the size of Djibouti. Right? Maybe not quite, but it's close enough for government work anyway, right? 10 to the 33rd is about the size of Djibouti. OK, 10 to the 34th, what do you need? 10 Djiboutis, right? Which is like not quite the size. Well, 10 to the 35th is 100 Djiboutis. That's like the size of Africa now. How much closer have we gotten to 76? We're not even halfway there in terms of the numbers here, right? We're already there. So that's Africa's is 36 we said was Africa's. So 37 is 10 Africas. That's like the size of the planet, right? Maybe not volume-wise, but let's say 38 would be, because that would be 100 Africas, which might fit in the planet, right? It's a lot of sugar, right? We're only at 38, right? So then you go 39, and now you need 10 Earths, right? 40, 100 Earths, right? 41, 1,000 Earths. We're talking about the size of the sun now, right? 42, 10 suns. 43, 100 suns. 44, 1,000 suns, right? These powers get huge, 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 right? So by the time we get to 76, you'd be talking about the size of the universe, right? And remember, the universe is relatively not very dense, I should say. Okay, so power, when you're talking about powers, you got to think, oh, 10 to the 23rd, yeah, well, that's huge. Remember, it's 1,000, 100,000 billion, and that's a lot. Okay, so that's how powers go up really, really fast. But I do want to show you powers. And I tell you what, I'll set it up during our break, which we're going to take in about 10 minutes. Okay. All right. How many moles of sucrose? Okay, so we haven't really gotten into the details of this, but maybe we can figure this out. How many moles? We did this yesterday, I guess. Moles of sucrose are there in 0.5 liters of 2 molar solution? Okay, we got to think about our formula here. If you don't know how to solve this, start writing down whatever you know formula-wise. What did we say the concentration was in? Concentration.
Moles per liter.
Moles per liter. Okay? So this is in moles per liter. 2 moles per liter. So if we put the concentration here, 2 moles per liter equals, we want to find the number of moles. We divide that by the number of liters we have, 0.5. Let me write it big up here. 2 equals the mass, or the number of moles, we'll say, divided by 0.5 liters. 2 moles per liter. How do we get the number of moles by itself? That would be 1. You multiply both sides by 0.5. 0.5, and you get 2 times 0.5, which is 1 mole. Right? So how many moles in sucrose in 0.5 liters of a 2 molar solution? Well, 1 mole. How many molecules is that? 6.02 times 10 to the 23rd, because if we know it's a mole, That's the number of a mole, 6.02 times 10 to the 23rd. We also covered this yesterday. Does a 1 molar solution, 1 liter of a 1 molar solution of sucrose in water have 1 liter of water, less than 1 liter of water, more than 1 liter of water? More than, what is it?
More than 1 liter.
The whole thing is 1 liter. So we've got 1 liter of liquid, and it's one molar solution. So does it have more? Does it have 1 liter of water, less than 1 liter of water, or more than 1 liter of water? Less than 1 liter of water. Why? Because the sugar takes up some volume, and the total is 1 liter. Okay, so you got less than that. Okay, let's see if we're right. 1 mole, we did that calculation. And a mole is 6.02 times 10 to the 23rd, and less water than 1 liter. Okay? All right. Okay. Now we got to talk about solubility. In fact, let's do this. Let's take our break now, and then I'll set up that Powers of 10 video, and then we'll go from there. So nobody should get caught in colors tonight. Okay, so I'm going to show you a little video that I just remembered. It's called The Power of 10. It's from 1977. That's how old this video is. I remember seeing it when I was in grade school. That's how old I am. But I guess you guys could have seen it in grade school too. But it's actually pretty cool. It's all about this stuff we were talking about with powers of 10 and how much things change when you talk about them. Yeah, it looks pretty modern.
Lakeside in Chicago was the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now every 10 seconds we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Power boats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1 million meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the Sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the Sun, followed by the massive outer planets, swinging wide in their big orbits. That on orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth.
This squares 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The two little satellite galaxies of our own are the clouds of Magellan, 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we'll appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic. Ten to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon a vast inner space. At last, the carbon nucleus, so massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons.
Oh, it's an exercise? Okay. That's an actual.
It said in the event of an actual hazard.
Oh, all right.
and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding. Are these some quarks in intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
Pretty cool, huh? Not bad for 1977. All right. Hit the lights again. You know how long it took that spaceship to get all the way out there?
I was wondering the same thing. Long time.
That was 1977 computer graphics right there.
What?
Yeah, well,
It
it was.
just space.
It was not a picture from the edge of the universe. All right. Oh. There we go. All right. So, let's see. There we go. There we go. All right. So, any questions on that Power of 10 video? Kind of cool stuff, if you ask me. Cool stuff. All right. So, now we've got, we're going to go back to solubility for a little bit. Okay, solubility, remember, the ability for a solute to dissolve in a solvent. So it's the amount it's how easy it is to dissolve something, in particular, whatever you're talking about. Okay, here's the sucrose, by the way. This is the whole, that's one sugar molecule. It's got lots of carbons and hydrogens and oxygens. And that's it, actually. Carbon and hydrogen, oxygen is all that makes up a sugar. Pretty cool, huh? In this case, it's got 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms in a pattern that looks like that. Okay, that's sucrose. Excuse me. What determines solubility is actually the attractions of the particles within the solvent and the solute. Okay? The attraction of those particles to each other. Go into some of that here. Some solutions actually won't saturate at all, in fact. Remember before we talked about when you mix alcohol and water? Okay, you can keep mixing, you'll never get a saturation. You'll just keep, it'll be forever soluble. You can actually add enough alcohol to the water that eventually the water becomes the solute and the alcohol becomes the solvent by number of molecules. Gases are generally infinitely soluble. There's enough energy there that they're not really you're never gonna get precipitation out of a gas, which would be kind of weird. Other solutes have very little solubility, like oxygen in water. It's actually difficult to put oxygen in water, which is part of the reason that fish could drown. If you turn off that little aerator in your aquarium, fish eventually decide they want to swim on the surface, and then they stop swimming, right? So because they die, you do have to kind of keep pumping. And I don't know if you've ever noticed the aquariums that have the little aerators in there. They're constantly pumping oxygen in there, right? There's lots of bubbles and lots of bubbles. Only a very small portion of those actually go into the water. Okay. 0.004 grams of oxygen in 1 liter of water. That's it. But it's enough for the fish to deal with. So there you go. A material that does not dissolve in a solvent is called insoluble. Makes sense. Okay, sand and glass, you can't dissolve those in water. You can stir all you want, not going to dissolve. Okay. We talked about this briefly the other night. There we go. We talked about this briefly. Solubility generally, not always, but generally increases with increasing temperature. In other words, it's easier to, what's that?
Like easier to dilute something?
It's easier to dissolve something the more temperature it is. And you know this if you took, you ever tried to make like a mixed drink with cold water? You can stir and you can stir and stir and stir and stir, and you'll never get all those crystals to go into the drink, right? You have to like really shake it a lot. But if you try the same thing with hot water, no problem at all. It just dissolves right away, okay? And the reason this is going on, what happens is because each molecule, the molecules have lots of energy, and in the water molecules, all that energy means they're striking the crystals, and they have more of a tendency to break those apart, which is what or break the individual molecules from their bonds with each other. Okay? And this is just a little picture of solubility. Let's see. For NaCl, well, it's about the same. It actually isn't changing much. For some of these other things like, what is that? Sodium nitrate, I think that is. As the temperature goes up, the solubility gets much, much greater. The temperature goes up, solubility goes way up. Okay? So gases are the opposite. So yesterday, I think I misled you when I talked about, I think there was a question on the lab yesterday about carbon dioxide in water, right? As temperature increases, carbon dioxide is less able to go into the water solution. So if you've ever noticed on a hot day, you have a soda, it loses its fizz quicker on a hotter day than if it was colder. Okay? And if you want to keep it fizzy for longer, put it in the refrigerator, right? Because it's going to lose the carbon dioxide less quickly. Okay? You can increase, especially for like liquid and gas, you can increase the solubility by pressurizing it. So in the soda bottle, right, you've got the carbon dioxide, you just keep pumping carbon dioxide in there and increase the pressure on top of that liquid, and you get more carbon dioxide to go in there. And then when you put the top off, you go psh, and what's happening is that little pressurized layer gets depressurized, and that's when the bubbles start coming out, because there's less pressure and it's super saturated at that point. Okay? So soda bottles are kept under pressure, so more carbon dioxide. Anybody have those soda bottles that you, or you can make at home? One of those home ones? I don't have one. Friends might have that. They love it. But they can't quite carbonate it as much as like you'll buy from the store. It just doesn't work that well. OK, so the next little topic is about soaps and detergents. Okay, the book actually calls dirt and grease grime, and I don't think that's a technical term, but maybe it is. I don't know. The book kind of talks about that. But dirt and grease together is grime. Doesn't come off with water, right? If you've ever like worked on your car or whatever, right? You get grease all over your hands. Water's not going to do a thing. You can rub water all day without some of that like hummus base, that Gojo. Gojo works great, right? Without that stuff, you're not going to get it off. The reason, okay, is because it's actually water, which is a polar molecule, which we've talked about, doesn't actually latch on to the grime, and so you can't get it off. Now, if you do want to get Gojo? Yeah, Gojo works well. That actually combines a detergent and an actual physical structure that like rubs it off your hands, right? The pumice in there. It's like sand. Yeah, it's like sand. You can also use a non-polar solvent like turpentine. I've never used turpentine before. It's a little like gasoline. It's flammable. It uses thin paint with turpentine. You can use that on grime. It'll come right off. It's pretty cool. Okay, but it also happens to be not so good for you, so you want to be careful with it. But you can do that. For clothes, though, we don't want to dip our clothes in turpentine, right? But we use soap, which soap is interesting. It has a polar side and a non-polar side. So if you take a look at this, okay, soap are these long chains of molecules. Okay, they got these big long carbon-hydrogen chains on the end of them. We'll get into more details about what that is. And then on one side, they've got something else that is actually creating a nice polar part of the molecule. Okay, in this case, this soap has a little sodium on the end of it there. Okay. If you ever noticed, there's baking soda based toothpaste and detergents, right? That's coming from the fact that there's sodium in there. Okay, sodium, right? And so anyway, there's a little polar molecule there, which actually is pretty good about grabbing onto the water. Because remember, water's polar, and this end of this soap is polar, so those two hold on to each other. I think the next slide shows this. And the non-polar part is good at dissolving the grease. So what happens is the little non-polar part dissolves around the grease and connects to the grease, and the water takes this end and whips it away. And all of a sudden now you've got soap and water, and you've got this grime away from your clothes because of the detergent. Okay, there it is. You can kind of see it here. This is not the greatest. Well, it's all right. Here's the grime. These are the non-polar parts of the molecule connecting to the grime because it's good at that. The polar parts are getting pulled away by the water, and therefore the grime comes off whatever your clothes are. Pretty cool. Okay, so that's why soap does its job. All about like long chains of one side polar, one side's not polar.
It looks like a war scene. You have the little soap dudes going up against the grime, and then
It does look like a war scene. You know what it also looks like is when your white blood cells attack like pathogens in your body. Kind of they go after it at once. Kind of cool. Okay, so that's soaps. Detergents, by the way, there were no detergents before about 1947 or so, at least according to your book. The detergents were created in a laboratory to have better properties than your average, like biologically based soap. Kind of cool. Okay. All right. I thought I'd throw this one in. Talks about this in the book. Okay, you go out to these water ice boxes around camp with the waters in them, right? You know they all have stenciled on there. No potable or potable.
Non-potable.
Potable or potable. I guess you can pronounce either way. Potable. Non-potable ice. What does that actually mean?
Don't drink it. Ice is made out of non-potable water.
Yeah, which means non-potable means don't drink it. You can't drink it. It's not good for you to drink. Now, I actually believe that all the water on base now is actually potable, so I don't think they're going and finding other water to make the ice with. So it's probably not. It's probably they're old, those stencils. So I don't. It's probably okay, but you're not supposed to take the ice and like put it in your. We don't get the ice from base? Oh, no kidding. Oh, all right. Well, there you go. There's not. It isn't potable ice, I guess. From the ice. The non-potable ice factory. But anyway, potable water means, or non-potable means you can't drink it. So we try to make it potable by doing something to the water and purifying it. Okay? Here's one way to purify water. Okay? Boiling it is, well, you can distill it, which we talked about a little bit earlier, but this is one way to do it here. And if you have a lot, this is probably the easiest way, and it's not going to be perfect, but it's going to be all right. You remove the dirt and pathogens, in other words, the bacteria and that sort of thing. Okay? You can mix the water, this is dirty water, with what's called slaked lime, and I'm not exactly sure what it is, but it's a chemical, add to the water, or another chemical called aluminum sulfate. Okay? You mix it together. Okay? What happens is those chemicals, they pretty much grab onto all the dirt and pathogens and then sink to the bottom of the container. And then you skim off the rest from the middle and top of the container. Okay, so let's see. It says here, the slaked lime aluminum sulfate added to the water reacts to form a gelatinous aluminum hydroxide. Okay, it's like, sounds gross, right? But what that's doing is that's taking all the dirt and grabbing onto it and that turning into that gelatin. Okay, and then it says impurities are captured by the aluminum hydroxide as it settles. And it's this little equation here. And then you end up with the gelatinous aluminum hydroxide impurities on the bottom. Then you can get the cleaner water from the top. Okay, it's not perfect yet. Then you actually aerate it. So just like your aquarium, you'll push air through it. Okay, what's happening there is that's actually kind of forcing out of solution some of the things that aren't very nice in water, that smell bad, that this process didn't take care of, like sulfur compounds. Okay? Yeah?
There's this town where I'm from that anytime you go into the town, you could already smell the sulfur.
Yeah.
Like, it was horrendous.
Yeah, I grew up actually right next to a lake that was a beautifully pure lake. In fact, we had a pipe that went from our house into the lake, and it had a little filter on the end, and my dad used to say that the filter was there to keep the frogs and the fish out, because it would suck the water in and we'd drink it straight from the lake, right? But in the winter, when the lake froze, you couldn't do that. So we did have a well that we dug next to our house. Unfortunately, the well wasn't nice and pure. It had really sulfur in it. So we had to have a purifier that would dissolve. And every so often it would break and it would smell terrible, but it was still fine to use, but it would smell terrible. You could boil that water and the sulfur would actually sit on the bottom, and then you could take the water. But anyway, so you aerate it. And then you disinfect it with some either ozone, but you didn't know ozone was a disinfectant, or chlorine, like you do. Okay, so if you go to big cities, the water sometimes tastes like chlorine. That's for two reasons. Number one, they're purifying it. Number two, good for your teeth, I guess. Well, I guess they add fluorine not chlorine. Anyway, you can still separate it out in the end, but that disinfects it, kills even all the other things. So that's one way to purify water. Okay, it does use chemical processes to do that. Okay. Or I found this recently. It's kind of tough to see what's going on here, but these kids
Like zombies.
they're just kids. They're
zombie kids.
they're not zombie kids. They are kids that are drinking from a rather dirty area of dirty pond of water, but they've got these little things called life straws, and they're about this big, and they're kind of thick, and you just drink through them, and they'll purify salt water. You just drink through it, and it'll purify salt water. Although they say they don't last as long if you do that. But this is what it says about them. Life straw contains Purotech disinfecting resin. I don't know what that is, some high-tech something or other. A patented, extraordinarily effective material. It kills bacteria on contact, and it also has textile pre-filters that are used to remove particles up to 15 microns. 15 microns is very small. Okay, we already saw in the video that a micron is 10 to the negative 6th. So 15 times 10 to the negative 6th size particles, very small particles. It will filter those out. Okay? And it also has the ability to filter out like parasites and things, which might be even smaller with some carbon in there too. So anyway, you can give these out or buy them for people in areas that don't have pure water, and then they don't die as often, which is a good thing. Okay? All right. We can also get rid of salt in water. Now, if you live in Djibouti, there's not much actual like water, except maybe once every 5 years when we get 7 inches, right? There's no water that's pure already or non-salty, so we have to desalinate. Do we desalinate on base here? I think we probably do. Kind of have to, I guess.
I don't know what the dispenser.
I don't know what we have here. But you can desalinate water in a couple of different ways. You can do it by distillation, which we kind of talked about a little bit earlier. These are actually kind of cool. This is a little distiller for the home. And all it is you have a bunch of water in here, like salt water. Okay, and if you live in Texas, where these things happen to, they have a lot of these over there, you can get salt water right there from the Gulf of Mexico, right? Salt water, okay? And this little glass piece keeps it warm in there because of the greenhouse effect, okay? And it evaporates the water. And the water comes up and onto this glass piece up here and then slowly drips down into the little freshwater piece down here. And then you can use that fresh water. And it says, this one doesn't say. I think in the book it tells how many liters a day you can get from this. But it's enough for a family. So no need to worry about desalinating lots and lots when you can do it just at home like this. Pretty cool.
They use like a smaller version of that on like survival rafts. They have this little thing they fill up.
They do. On survival rafts, they do have that. Survival rafts, you have just little distillers like this. You also have like rainwater capture devices to capture the rain. But yeah, if you're ever stuck on a life raft, don't drink the salt water because you'll die real fast.
But if you have one of those stick things.
If you have one of those sick things, maybe they should start putting those in there too.
Yeah. The most common one now for households, they have RO units that it attaches right to the water line coming into the house.
Is it salt water coming into the house or purifier?
It's just
Oh, purifier, yeah. They have purifiers come in, right. That makes sense. Makes sense, yeah. Okay.
But it's the same concept with the RO.
Got it.
Like that.
Anybody ever been on a submarine?
No, thank you. Submarine.
Nobody else been? I've been on a submarine. Now, a submarine, they desalinate the water using reverse osmosis.
Most ships have.
Okay. Most ships have now too? Okay, same thing. Yeah, ships do too. What this means is they're actually basically pushing the water molecules through a semi-permeable membrane that they make out of something. I don't know exactly how they make it, but you might have, if you ever took biology before, you might have heard of osmosis, which happens in cells, right? And what's going on is you've got this membrane here that allows water to flow from one side into the other, right? If on one side you have like fresh water and the other side you have salt water, it actually allows, see how there's basically you can think of it this way. There's more molecules of fresh water over here, and more molecules are going to hit this little membrane from this side than from this side because the big one's getting away from that. And so actually, this actually means more fresh water will end up over here in the saltwater part. It's actually not what you want. Okay, this is osmosis. If you set this up, you'd end up with more salt water and not less, right? Which is not what you want. So what you do is you do this thing called reverse osmosis. And what's happening in osmosis, it's actually because of the more fresh water is coming on from this side to this side, you end up with a slightly, if you drew this thing like this, you know how water, we talked about at the beginning of the year, finds its own level? Well, if salt water is on one side and fresh water is on the other, it actually makes the level a little bit different, as it turns out, right? Because of this osmosis that's going on. It's pretty cool. Well, what you're trying to do is you're trying to force the fresh water back over to the other side. So what you do is you provide pressure down on this side. In fact, you have to do a lot of pressure, 25 times the atmospheric pressure. That's a lot. Okay, you have to press down really hard, and the fresh water will start to go from the salt water into the freshwater side, and then you're good to go. Okay? Well, it's really hard to do that. Engineers are smart enough to figure that out. It takes a lot of energy, but you can do it. And so if you're in the middle of the ocean, either on a submarine or a surface ship, you have these desalinators in there. They use this reverse osmosis, and you get your fresh water. That's how they get it. And by the way, once they get that fresh water, they then treat it with, with chemicals as well, but they also treat it, they also put minerals and things in it. The one ship I was on, you guys know about hard water versus soft water? I think I didn't put that in here, but the book talks about hard water and soft water. Hard water has, let's see, not enough minerals in it, I guess it is. And it it's hard to, I don't even know how to put it. It doesn't, like you can do your hands together under the water and it doesn't feel like you can, it kind of sticks a little bit.
Now here we have soft water.
We have pretty soft water here. You know how you go to like Combat Cafe and it takes like 5 minutes to like get the soap off your hands after you do it? It's because the water's too soft and it actually doesn't bind very well to the soap and doesn't come off. So, but it's because they've added more, they purified it, added more things. Okay.
So that slick feeling from soft water and soap is because the soap is still on you?
Yeah.
It drives me nuts.
It is, yeah. It's because the soap's still on you when you get slick like that. Yeah. Like I said, I don't know, for whatever reason, the Combat Cafe seems worse. I don't know why, but it seems worse. Anyway.
And RO is considerably more efficient than evaporating.
Reverse osmosis is more efficient than some other methods that we do. Yeah, distillation. Distillation's generally more expensive, although I think, if I'm not mistaken, countries that do this, like Saudi Arabia, gets almost all their water from desalination plants. I think they use distillation to do it.
The golf course in Doha, Qatar.
Yeah.
They have their own plant.
The golf course in Doha, Qatar has their own plant to desalinate.
Yeah.
Hey,
Water at the golf course.
probably costs $50,000 a year to be a member of the golf course. Who knows? Okay, so that was chapter 16. Chapter 17, how chemicals react. Now, you could spend months. I've said this for a lot of different chapters, but you could spend a long time learning about how chemicals react in if you really got down and studied it. We're not going to go into too many details. I think next week we'll probably do a few formulas and maybe balance a couple equations or whatever. But I was thinking about the other day. I'm like, okay, so look, I'm an engineer. I've done like this stuff for a long time. How many times have I ever had to balance an equation outside of class? Never, right? Never. So we might talk about it a little bit, but we'll stick to mainly concepts. Right, Louis? Right. All right. Okay. Question. How can 50 grams of wood burn and produce more than 50 grams of product? Excuse me.
Density of the product is
The density of the product? So you've got this piece of wood, right? You got this piece of wood. There's a knot in the middle of it right there, and you're going to burn it. Okay, and this piece of wood has 50 grams of mass. Once you burn it, you add up all the pieces of ash, and you end up with 60 grams of ash. What's the deal there? Did we create matter?
Is it reacting to the air around it and creating different things?
Anybody know what fire really is? Like how fire happens? We should do a whole couple minutes on fire. Yeah, what is fire actually doing?
It's a chemical reaction.
It's a chemical reaction. It is indeed a chemical reaction. When the wood gets hot enough, right, it starts reacting with what in the air? Oxygen in the air. Okay? And that reaction makes byproducts like soot and smoke and ash and all that. And in fact, the ash here is actually, in most cases, more massive than the actual wood was because it's got some of that oxygen stored in it now. Pretty cool stuff, right? I have another question kind of similarly related. A tree. Where does a tree get its mass from? Like, it starts out as a seed, right? And then like a week later it's a little seedling, and then a month later it's a little tiny tree, and then like a year later it might be this tall and whatever, and then 100 years later it's this giant tree. Where did it get the like you go and you saw it down, and that wood, where did that wood come from? The ground? Water? The sun? Well, kind of. You're kind of all very close, but nobody said exactly what it is. What the main part, a component of wood is.
Carbon dioxide?
Ah, there we go. Carbon dioxide, which it doesn't get from the ground, and it doesn't get from the sun. It gets it from the air, right? In fact, the trees are really the reason that we have as much oxygen as we do, because their byproduct of photosynthesis and so forth is oxygen, right? But it gets its mass from the carbon dioxide in the air. So a tree is mainly made up of product from the air. You get some minerals and water and stuff from the ground, but most of it comes from the air. Pretty cool. Okay? All right, so anyway, yes, when you've got chemical reactions happening for wood, so you can end up with more byproducts than you started with. You didn't create matter, you just got it from the atmosphere. Okay, let's do a couple little things on chemical reactions here. Chemical reactions, when you have a chemical reaction, you get new compounds that are formed. Okay, you could be breaking things up into other compounds. You end up with starting with one compound, ending with another compound. Remember how we said there's physical changes and chemical changes? Chemical changes, you end up with something completely different. Okay, so you start with take a look at this one. You start with 2 hydrogen 2 molecules. Okay, so those 2 guys together are a hydrogen. 2 hydrogen atoms, they've got a bond, and they're floating around the atmosphere. Okay, 2 of those, 1 oxygen 2, okay, which is 2 oxygen atoms together. You mix them together, you end up with 1 molecule of water and another molecule of water. So you end up with 2 molecules of water. Can you look at this and see that we haven't created or destroyed any atoms here? Right? We started with 1, 2, 3, 4 hydrogens, 1, 2 oxygens. We end up with 1, 2, 3, 4 hydrogens and 2 oxygens. Okay? And when we say this is balanced, what we mean is just that. We have the same number of atoms that we started with that we end with. Okay? So if you look, 2 hydrogen 2s plus 1 oxygen 2 gives you 2 hydrogen dioxides. Right? I'm sorry, not hydrogen dioxides. Dihydrogen monoxides, right. 2 water molecules. Okay, because the same amount. The 2 outside here means that you've got 2 times whatever this amount in there is. So in this case, we've got 2 hydrogen 2s, so how many total hydrogens? 4. And we've got 1 oxygen 2, so how many total oxygens? 2. And over here, we've got 2 hydrogen 2s, so we've got 4 hydrogens and 2 oxygens, just 2, right? So we didn't create any new matter or destroy any matter. The ones on this side are called the reactants. This side, they're called the products. Okay? And that's all chemical reactions are. Now, you can actually, this can get very, very complicated when you have big molecules and different types of molecules. Okay? But we're not going to worry about a lot of those details. Okay? All right. So chemical equations. When we talk about chemical equations, okay, we've already said this. You still have mass conservation. You don't destroy any atoms or lose any atoms during a reaction. Okay? Now, we do have law of mass conservation. There is some energy involved, which we don't need to worry about too much. But when you break and combine bonds, you actually turn some mass into energy or turn some energy into mass. It's actually kind of cool when that happens. But in terms of the larger part of the picture with the atoms, you're not destroying or creating any atoms. Everybody get that? Okay, that's an important one. And by the way, yesterday when we were talking about Remember this formula, C1V1 equals C2V2, right? That was all about conservation of mass. Okay, when we knew that we had a certain volume and a certain mass, and we ended up with the same concentration in the end, or same relationship at the end. That's because of the fact that you've got mass conservation. Okay? The number of times atoms appears on one side of the equation before that arrow, and when we do chemical equations, we do arrows on here. The number of times the atoms are over here is the same on the other side. Full stop. Okay? All right. Okay. Now, this is actually probably a little premature for a check question, but let's see if we can figure this out. Is the following, well, I think we can figure it out. Is the following chemical equation balanced? Okay. Let's count up the number of atoms. Okay, I'll put them up here. How many carbons are on this side? One carbon. So one carbon. How many hydrogens? 1 times 4. 4 hydrogens. Okay. How many oxygens?
2.
Well, careful. 2. 4 oxygen atoms. 4 oxygens. How about the other side? How many hydrogens? 4 hydrogens. How many? Check. So we're good, right? 4 oxygens. 2 times 1 plus 1 times 2 is 2 plus 2. 4 oxygens. We're good. And then how many carbons? 1 carbon. And 1 carbon. So we're good. Is it balanced? Yes. Okay. Again, in a lot of classes, I would say, balance this equation. And then I'd leave these parts blank. And you'd have to figure out, OK, if I'm going to need, if it's going to be H4, I'm going to have 2 there, H2O, et cetera. And it's a little tricky. There's actually formulas you can use to, like algebraic ways of doing it so that you never mess it up. But it's still tricky. Okay. So the answer is what? Is it balanced? We said yes, so it's not any of the no's. Yes, because the coefficients on each side add up to the same number. Well, 1 plus 2 and 2 plus 1. That's true. Is that why it's balanced? No. Yes, because the same atoms appear before and end. Before and after. Ta-da! There we go. OK. Let's see. I think I have another. Well, not quite yet. Thought I had another check question. Counting atoms and molecules by mass. So this, I mentioned this. Well, I guess I didn't mention this before. This is slightly different than what I was talking about with the sugar and water. But chemists actually need a way to mathematically express a chemical equation. Well, the periodic table, which you guys all have now. OK, take out your periodic table that I gave you at the beginning. Anybody not have it? OK. If you look at the periodic table, it gives the formula mass of the elements. Does anybody remember which number down there was the mass?
The average atomic mass?
Yeah. The bottom one. And it says, because there's a little legend on here that tells you this. I will give this to you on the test. Right? At the end of the year, I'll give you this little periodic table. OK? So yeah, if you look, it's the number right at the bottom that tells you the atomic mass of an individual atom. Individual atom. OK? So if you look here, carbon, right, has a mass of about 12. OK? Carbon has a mass of about 12. OK? And we're just going to round all these things. In fact, actual chemists, when they do these balancing things, they just round as well. So you don't have to worry about all the little details. Just round to the closest number. OK? If it's exactly in the middle, I don't know what you do. But you have to know which type of isotope you're talking about. OK? Carbon, 1 molecule. Oxygen, 2. So O2, what's the atomic mass of O2? Look on your sheet and tell me. It would be 16 each. You're rounding.
32.
Right? So it's 32. Yeah. So oxygen, 32 is the amount there. OK? So that's the mass. Yeah?
Question.
Yeah.
Like beryllium and scandium.
Beryllium, yep.
Like beryllium says 9.012, and then what's the 182?
I think that's just like a comma. You know, like how you do, you do like 1,000 and you put a comma in there. I think it's just spacing it out so you know where the space comes. I think that's I think is it always, is the little space, where's the other one?
The sodium.
Yeah, you look at sodium. So it's got 3 after the decimal, and then they do a little space, then they do 3 more, then a little space. the reason some of the numbers have lots of decimals after them and some of them have fewer is because we know more about those. We've been able to measure them more precisely, right? So we know, how much of a certain atom we have in the atmosphere, and we can figure that out. Okay, so we can use our periodic tables to tell us the actual masses of each individual atom. Okay, and what you can do is you can look on here and you go, a carbon atom. This is tough to see. A carbon atom is 12/32 or 3/8 as much as massive as an oxygen molecule. Okay, so if you had the same number of molecules of carbon and the same number of molecules of oxygen, oxygen would actually weigh more. But actually, if there was 3 grams of carbon, you'd have 8 grams of oxygen. Okay? Yeah. Right? But that's pretty, that's a lot of oxygen they jam in there, too. I mean,
I don't think those drawings are.
That's probably compressed. Well, it could be to scale. I mean, it depends. Carbon's not that heavy if you've ever seen it. I mean, it's not, sure, it might not be that high up in there for 3 grams of it. No, not that much, but it's not too bad. Not too bad. Okay.
So these readings are per gram.
These readings are actually, it's not per gram. It's saying it's per mole. Right? Okay, so 1 mole of carbon atoms is 12 grams. 1 mole of oxygen by itself would be 16 grams. 1 mole of oxygen 2 is 32 grams, etc. Okay, so that's how we do that. Tell you what, let's take our next break now. I see some dying eyes here, and we'll do that. We'll take our break now, and then come back in about 10 minutes. Come back right at 7:15, and then we'll finish up. So I found another video by Mr. Anderson. I'm going to have to write him an email and say that you guys liked his stuff. If you like this one, we'll see. This is on how to balance chemical equations.
My beginner's guide for balancing equations. The first thing that I want to let you know is that there's no magic to balancing equations. There's no secret that you can somehow pick up and all of a sudden become a guru. The reason I made this video is that some students just seem to struggle with how do I even do that, or the concept behind it. And so if you're really having troubles, hopefully I can kind of clear some of that up. And if you're not, this is probably not the video for you. I would just go Google balancing equations practice, and you'll find some really hard ones out that you can try your hand at. So let's get started. We're going to start. The first one we're going to talk about is the combustion of hydrogen. This is the Hindenburg explosion, and after this we quit putting hydrogen gas into blimps for obvious reasons. But essentially what happens is hydrogen combines with oxygen. Okay, so if we look at the equation down here at the bottom, the equation as it is H2 plus O2 yields water, or H2O, and we're going to get a lot of energy out of there as well. Now, the first thing we need to talk about is what these numbers actually mean. So this 2 down here is a subscript, and that means that it tells you how many atoms of hydrogen are in a molecule. And so this is what the molecule of hydrogen would look like. We're going to have 2 atoms of hydrogen. The thing that you need to remember is that you can never change the subscripts. Subscripts have to remain the same, because if you change it, you're changing what that molecule actually is. And so this would be H2, this would be O2, so we have 2 oxygen molecules attached together. Then finally we have H2O, and H2O is 1 oxygen and 2 hydrogens on either side. And so when I look at this, a lot of people will just try to go and answer this, but maybe we need to step back a little bit and actually look graphically at what's going on here. And so when I look at this, I can see here's reactants before the reaction and products. And so just looking at it, when these are graphically shown, you can see that I have 2 of these red oxygen atoms on the left side and only 1 on the right. And so the first thing you might want to do is kind of double that. And so let me do that. Okay, so now visually we've got 2 water molecules, and so I've got 2 reds on the right side and 2 reds on the left side. You'll also notice, so that's balanced, that the hydrogens are changed. And so I have 4 hydrogens on the right side, but I only have 2 on the left side. So now let me click it again, and we've got a balanced equation. In other words, I can never change the subscripts, I can never change what these molecules are, but when you're balancing equations, what you're trying to do is add more of the molecules so you can see that reactants and products will be balanced. Okay, now how do we actually write that out? So we can put in front of here what are called coefficients, and coefficients are numbers in front of the molecule. It tells you how many there are. And so there is one oxygen, and we never write the coefficient of 1. And so you don't want to write 1 as a coefficient. If it's a coefficient of 1, you just leave it blank. But let's go over here to H2. You've got this H2, that H2, and so you have 2H2. So that would be on the left side. If we go on to the right side, you have this molecule of water, this molecule of water, and so we have 2 molecules of water on the right side. And so if we step through this, this means we have 2 molecules of H2, so that would be 4 hydrogens on the left side. After you balance an equation, you want to go back and look at it and make sure it's balanced. Over here we have 2 H2s as well, so we have 4 hydrogens. We have 2 oxygens on the left side, and we have 2, this coefficient multiplies times this whole thing, so we have 2 oxygens on the right side as well. And so we would call that a balanced equation. And so hopefully just by looking at it graphically, that might help a little bit. Let's go to the next one. Next one in a chemistry lab is, you see it all the time. This is a Bunsen burner, and these are some flames from a Bunsen burner. And so a Bunsen burner works using a gas called methane, and methane is CH4. So if we take a look at methane, methane looks like this right here. It's got 1 carbon molecule, and then it's got 4 hydrogens attached around the outside. And when we burn methane, what that really means is that we're combining methane with oxygen, and we're creating these two things. In complete combustion, we're creating some carbon dioxide gas. That's 1 carbon, 2 oxygens. And then we're creating a little bit of water. The other thing we produce is going to be energy. Okay, so if you look at this, just graphically on the left side and on the right side, the first thing, at least to me, that jumps out is that there's way more hydrogen on the left side than the right side. So the first thing I could do would be to add another water on the right side. So if I've added another water on the right side, the yellow balls on the right now match the yellow balls on the left. The carbon, there's only 1 on the left, matches the 1 on the right, and so we must be getting really close. But I've got 4 reds on the right, and I only have 2. And so I have to add that as a whole molecule. So if I add 1 more molecule of oxygen, now we have a balanced equation. So how do we write that out? So methane on the left side, I have 1 methane, but I'm not going to write the number 1. How many molecules of oxygen do we have? We have 2. So I'm going to put a 2 as a coefficient right here. Now on the right side, we only have 1 carbon dioxide, so I'm not going to put a 1, but there should be, in your mind, a 1 there. And then how much water do we have? We have just 2 waters. So I'm going to put 2 right here. Now we could go through the whole thing. So how many carbons do we have? 1 on the left, 1 on the right. How many hydrogen do we have? 4 on the left. And this 2 is multiplied the subscript, so we've got 4 on the right and 4 on the left. And then if we look at oxygen, we've got 4 on the left. And then we've got 2 oxygen here, and we have 2 oxygen there. And so when I'm solving and trying to balance equations, I'm not really seeing these, but if that helps you visualize it, then it'll help you do better at that. So let's try it. So the only way to get better at this is to just practice. And so let's try a few, and I'll show you how I would think through this in my mind. So if we look at the first one, this is H2O2, which is hydrogen peroxide. Breaks down into hydrogen gas and oxygen gas. Okay, so how would I set this up? Well, on the left side, we've got H2. So if I want to write it out, I could. So I've got 2 hydrogens on the left. And as far as oxygens on the left, I've got 2 oxygens as well. And so on the right side, how many hydrogens do I have? I have 2 on the right, and I have 2 on the left as well. And so this already is a balanced equation. And so what do you do if you find a balanced equation that's already balanced? You don't do anything to it. In other words, we'd write a 1 in front of each of those, but we never write 1s, and so I'm going to leave that 1 the way it is. Let's go to the next one. On the left side, we've got sodium, we've got chlorine gas, and then we're making table salt. And so if you want to write this out, you could. We've got Na, and I've got 1 of those. I've got chlorine on the left side, and I've got 2 of those. So that's on the left side. That's on the reactant side. Now let's go to the product side. How many sodium do we have? We only have one sodium. And how many chlorine do we have on the right side? Well, we only have one chlorine. So that's a problem, because on the product side, we only have one atom of chlorine. And on the reactant side, we actually have two. So how could I fix that? Well, let's try to go back. Let's say I've got too few chlorine on this side. So let me just try and add the next step, which is to add a 2 on the right side. So by adding a 2 on the right side, I've taken care of my chlorine. So on the right side now, I have 2 sodium and 2 chlorine. But I've set up another problem. In other words, I have 2 sodium on the right side, so now I have to balance that over here. So I'm going to come back here and write a 2 over here, which that makes this a 2. Okay, so now we've got 2, 2, 2, 2, and that's balanced. And so the right answer for that one is to put a 2 in front of the sodium and then a 2 in front of the sodium chloride. And that's a balanced equation. Remember, you can never change the subscript. All right, let's do another one. Another one. And so these are getting progressively harder. And so I'll give you some tips as far as that goes. The first tip would be this. If we look at this one, we've got silver sulfide, silver, and then sulfur. And so this 8 jumps out right away. So on the right side, I've got 8 sulfur atoms. If we look on the left side, I've only got 1. And so as a bare minimum, I'm going to try writing an 8 right here. Let's see what that does. Well, now we have 8 sulfur on the left side, 8 sulfur on the right side. But our silvers aren't matching. So on the left side, we actually have 16 silver, but on the right side, we only have 1. And so let me just try writing a 16 down. So now that's a balanced equation. So we could go through 16 silver, 8 sulfur, 8 sulfur, and that's going to be a balanced equation. The nice thing about balancing equations is you can always check it at the end and you know that you are right. It's not like you're maybe right. You absolutely are right as long as you're just adding the coefficients. All right, so here's the ones that are more likely that you're going to find. And so let's work through this and always be patient, remembering that if you get frustrated, you can just erase them all, start over again. You should be able to figure them all out. It's just kind of a guess and check. But let me show you how I would think this one out. So we've got water, carbon dioxide, got a hydrocarbon here, and then we've got an oxygen. And so on the right side, the thing that jumps out to me right away is we've got 7 carbons on the right side. And so what I'm going to try to do is put a 7 over here. Okay, so what does that do for me? Now I've got my 7 carbons taken care of. The other thing that jumps out right away is on the right side I have 8 hydrogens, and water is the only thing on the left side that actually has hydrogens. And so if there's an 8 here, let me try putting a 4 over here. Okay, so what that does is give me hydrogen on the left is going to give me 8, hydrogen on the right side is going to give me 8 as well. Now I love it when I solve these and I get down to just like one thing left and it has 1 atom in it. And so I think carbons and hydrogens are good on either side, but let me take a look at the oxygens. On the left side we have 4 oxygens, so in this molecule of 4 waters. And then we have 14 here. And so I've got 14 total oxygens, 7 here, and then 4 over here. And so how do I get to, so again, I've got 18 total. And so if I were to put a 9 over here, that would give me, on the right side, 18 total oxygens. On the left side, 18 total oxygens as well. So that would be a perfectly balanced equation. And so that's kind of my starter's guide on how to balance equations. Remember, you can only add the coefficients. You can never change the subscripts. And if you can get confused, start imagining them as molecules and even draw them out if you have to, and that might help a little bit. So I hope that's helpful, and have a great day.
Is that helpful? I don't know. I'm not really going to make you do that much, so. But, excuse me. Okay, so let's go back here, and we'll go back to this, and we'll finish up. All right. Excuse me. All right. So we already talked about this. Let's go to the next one here. So when you count atoms and molecules, we generally do this part by mass. And this is where your periodic table is going to come in nice and handy. Okay? 22.990 grams of sodium is 1 mole. What does it say next to sodium on your table here? 22.989, right? Or 990 if you round. Okay, so that's going to be 1 mole. That's nice. Lead, nice heavy element, right? Kind of in the middle. Where's lead? Sorry, on the right-hand side in blue, it's 207, 1 mole. Aha. Helium, way at the top corner, 4.003, 1 mole. Aha. So this is how you read this. I kind of mentioned this earlier. The mass on here, the atomic mass on here, is the number of grams in 1 mole of that atom. Good?
But it's also the weight of an atom, like the protons.
Well, yes. If you, it's in some sense, it's the weight of the number of individual nucleons to around, if you round it a little bit. Yeah. So if you look at helium, it's 4, which is 2 protons and 2 neutrons. Yeah. Okay. All right. Okay. Oh, we already did this. Well, let's look at this one. This one's a little different. 2 hydrogen 2s. Well, you have 2 moles, that means, of H2. What do we say? What's the mass of H2? If you look on your mass here, hydrogen has, H1 has 1. So H2 would be 2. So that's 2 moles of H2 is 4 grams worth. So far, so good? Oxygens, 1 mole. Now, I know the guy in the video said you never write the 1, but we're just going to, it's there, right?
Hewitt.
No, it's the other guy.
Chemistry.
Right, it's a chemistry guy. Well, anyway, whatever. The 1's there. We just don't write it normally. 1 mole of oxygen 2. And oxygen has how much mass per mole? 16. So 16, if there's 2 oxygens, that's going to be 32 grams. 4 plus 32 is how many total? 36 grams over here. Well, you better end up with 36 grams over here if you counted everything, right? 2 H2s and 2 oxygens by themselves. 2 times 2 is going to be 4 plus 2 times 16, which is 32. 32 plus 4, still 36. See how the masses are the same at the beginning and the end? Okay.
So if you're working with something like carbon 14 instead of carbon 12,
if you were working with carbon 14, you would use 14 instead of 12, right? If you knew your substance was pure like that. Yeah. This is the averages, and that's why we round them as well. Good question. OK, check question. All right, you ready for this one? How many moles are in 45.4 grams of chlorine? And the hint is, this is chlorine, Cl2, chlorine gas. OK, how many moles do we want? We want the moles. OK. Well, it's not quite on this table. We got to do a little thinking here. Well, let's do a little thinking here. 45.5 grams. We might have to use a calculator too. 45.4 grams. Well, let's figure out the number of moles of 1 Cl2. Okay? All right? One Cl is 35. So 2 Cl's is going to be 70. So this is 70 grams per mole, right? And we have 45.5 grams. So if we want to do, we do 70 grams per mole, right? And we want to figure out how many moles there are. Divide which by which? But divide 70 by 45?
Correction. No, 45
Yeah.
by 70.
You have 45.5 grams, right? Divided by 70 grams per mole actually gives you the number of moles. So what's 45 divided by 5 divided by 70? 0.64 maybe? Let's see if that's right. I don't even remember if that's right. Ta-da, 0.64. OK, 0.64 moles. What's wrong?
What I did was I just added the 1 chlorine, which is 35, and then you add whatever you need left over.
Yeah, you can't do it that way. This is all about percentage because you have grams and you know how many moles per gram or grams per mole it is. Then you do that. You have to do it that way. OK, just a little math. Just a little math.
So why?
Yeah. Sorry?
When we're talking about gases like
Yeah.
oxygen or hydrogen or chlorine, we're making them O2, CO2, H2.
Yep. Why do they do that? If you have chlorine gas by itself, the molecules tend to form covalent bonds where they connect into molecules like that. The atoms will do that. A lot of gases will do that. Not all of them, but a lot of them will.
So don't always assume that there's a 2 right there.
Don't always assume there's a 2, yeah. Don't assume it, but you'll generally be able to figure it out. Okay, you ready? Here's another question similar. How many grams of water? So we're looking for grams of water. How many grams of water are produced from 1.25 moles of methane? And methane is CH4. Okay? So how many moles of methane do we have in this formula here? How many do we have here? We have 1 mole in the formula of methane. How many moles of water do we have here? 2 moles of water. So what's the proportion of methane to water? Yeah, it's a half, right? So to go from amount of methane to the amount of water, what do you do? Multiply by 2. So we are going to start with 1.25 moles of methane times 2 gives you 2.5 moles of water. Well, do we know how to figure out how many grams 2.5 moles of water is? I bet we do. Let's look. Water. Oxygen is what? 15. Hydrogen is what? 1. And how many of them do we have? We have 2 of them. Just 2 right there. Let's not worry about that. Just talk about the atoms, because we're just trying to figure out how much oxygen we have if we have 2.5 moles of it. Right? So 15, 16, 17 grams. Okay, that's 17 grams per mole. Right? 17 grams per mole. How are we going to get grams if we know how many moles it is total?
17 times 2.5.
17 grams per mole
And you have 2.5
times 2.5 moles gives you what? Let's see, 17 times 2 is 34, plus another 8.5. 45, is that right? 43 and a half? 44 and a half?
Because actually,
Yeah, 44 and a half.
16.
Oh, is it 16? Did somebody tell me it was 15? Oh, it's 16. You got to round up. 18, right. It didn't sound right. Okay, so this is 18. So 18 times 2.5. Well, 18 times 2 is 36. And 9 times plus 9 is 45. So it's going to be that, right? Let's see. Ta-da! 45. OK. I'm just showing you this stuff. I'm not going to say on the test, do this. OK? But come on, guys. This isn't that hard. Come on. With a little practice, you'd know how to do this, right? I'm just kind of want to show you the ideas here. OK? All right, so we got that one. Let's look, see if there's another one. Aha. All right. Whew. How many moles of carbon dioxide are produced from 50 grams of methane? All right, what's the first step? What are we going to look at here?
Carbon dioxide.
Let's look at the carbon dioxide, but let's look at the mole ratios here. What's the mole ratio of methane to carbon dioxide? 1 to 1. Woohoo. So really, we need to figure out how many moles of methane there are, or sorry, how many moles of methane, and that gives us the number of moles of carbon dioxide, because it's a 1 for 1. How do we figure out how many moles 50 grams of methane are? 50 grams of methane. Okay, start adding up. What's carbon? 12. What's hydrogen? 12. And how many hydrogens are there? 1, 1, 1, 1. 12, 13, 14, 15, 16. 16 grams per mole. And if we have 50 grams, how do we figure out how many moles that is?
16 divided by 50.
You know, you'd think it would be 16 divided by 50. But the problem is, so you can do what's called what's called dimensional analysis. And this goes back to fractions. OK, let's just do this real quick just to show you and get it on tape. So you can go back and look at it 100 times to get it. If you tried to do 16 grams per mole divided by 50 grams, what would your unit end up being? You can take units and do exactly the way you do it with math. You can cancel units out, believe it or not. It's cool. 16 grams per mole, I'll write it like this, divided by 50 grams. Well, whatever that number is, some number, let's say 16, I'll do it on your calculator. What's 16 divided by 5? 0.32. Grams is on top, on the top part of the top. Well, you have to flip the bottom one, right? So let's look at this. 16 grams per mole, right? And if we flip this over here, this is 50 divided by 1 times 1 divided by 50 grams. The grams cancel out. This is all stuff that I'm not going to make you do, but this is kind of dimensional analysis is a really important skill. The grams cancel out. You divide 16 by 50, you get 0.32. Well, what does happen to the moles here? Is it on the top or the bottom? It's on the bottom. So you'd end up with 0.32 per mole. That's not a unit of moles. That's a unit of per moles. Doesn't make sense.
So how do you convert it then?
You don't do this. We did it wrong to begin with. Let's look at it this way. Let's do it properly. 50 grams divided by 16 grams per mole. Now let's do this. It's going to be 50 grams divided by 1 times what? You flip it, right? 1 mole divided by 16 grams. The grams cancels out. What's 50 divided by 16? 3.13, by the way. It happens to be one of our answers. 0.32 is not. 13.13 is moles now on the top or the bottom?
On the top.
It's on the top, so 3.13 moles. Is that what we're looking for? That's what we're looking for. So it's probably the answer, right? Ta-da. OK? Now, this sort of analysis here is only is useful when you don't know if you're supposed to divide one by the other or the other by one. You can figure it out. You go, oh, if I do it this way, it comes out wrong. Like the units come out wrong. OK? And it's really important skill. And it's an important skill in a lot of things, actually. Remember how we did velocity equals distance divided by time, right? Units of distance are like meters. Units of time are seconds, right? Well, if you had, let's say we wanted to find out time, and we had velocity and distance. Time equals what?
Time times v equals v times 1.
Time times v.
Cross product.
Well, OK, right. So if we want d, what are we going to end up with? Or we want time.
D
It's
divided by v.
distance divided by velocity. But unless you did the algebra, you wouldn't necessarily know that. So let's just carry this one on to let's say you had 10 meters. OK, your distance was 10 meters, and you were going at 5 meters per second. How long would it take you? 2 seconds. You're going 10 meters, 5 meters per second. Takes 2 seconds. So you divide 10 meters divided by 5 meters per second. Well, what's time in?
So units of seconds.
Seconds, right? So we better end up with seconds being the unit that we end up with after this. Let's see. Let's just do it out. If we're going to flip this is really equal to 10 meters divided by 5 meters divided by seconds. If you flip this, that becomes 10 over 1 times seconds divided by 5 meters. 10 meters divided by 1 times seconds over 5 meters. 10 divided by 5 gives you 2. Seconds is on the top or the bottom? It's the top, 2 seconds. So there's your answer. Now let's look if we did it wrong. Let's say we forgot this formula and we said it was velocity divided by distance. Let's just say we did it wrong, right? Well, we said the distance is 10 meters, and the velocity was 5 meters per second. What do you do when you get 5 divided by 10? Half. And is that the right answer?
No.
If you're going 10 meters in 5 meters per second, does it take half a second to get there? No, it takes 2. So we're wrong. But let's see if it works out. The units work out. 5 meters per second divided by 10 meters is the same as saying 5 meters per second, flip this, 1 divided by 10 meters. Does the meters cancel out?
Yeah.
Yep. Does the second end up on the top where we need it? No, it ends up at the bottom. This actually, if you do 5 divided by 10, this is 0.5 per second. Right? Which is a little weird. Right? 0.5 per second. No, that's not right. Right? That's actually the frequency, if you want to think about it that way. 0.5 meters per second is what you're going. Right? Because you're going a total of 10 meters in 2 seconds. No, it's not right, actually.
If it's 10 meters per 2 seconds, it means 5 meters per second.
Yeah, it's 5 meters per second. You're right. It's 0.5 per second. It's not even. It doesn't even make sense. Yeah, it's just not even wrong. Or it's not even wrong. It is wrong. It's not even right. But anyway, the point is that if you do this dimensional analysis, in other words, if you use a little bit of math skills that you absolutely learned in class to figure out the ratios properly, you'll be able to figure out if it's divided one way or the other just by doing that. So it's pretty important stuff. Okay? All right.
But usually when you work with numbers, you don't put the unit though.
That's a problem though, isn't it? Because you should always put the units. Because then you can figure that stuff out. And you can do questions like, maybe I will ask you a question like this on the test. Not hard, right? Oh, come on. It's not that. It's not, excuse me. It's not that hard.
That's math. This is your next.
Just saying. I know, I want to stick to the concepts, but the point is, this stuff is not that hard. It's just you got to like practice it a few times, you know? So that's the way it is. OK. So only a few more things. When you have a reaction, it doesn't happen instantly. OK? Reactions do not happen instantly. OK? I wish we had more chemicals in here. I could show you a reaction where you pour a liquid into another liquid and it slowly turns purple. Right? It gets more and more and more purple over time. It's because the reaction takes some time to happen. And the reaction in that case would be turning purple. It's like, what was that last night? Manganese, or what was that? Something permanganate or something. I think that's the purple one. So the amount of time it takes is called the reaction rate. Okay? And we could spend all this time doing practices on figuring reaction rates out too. You probably did that in chemistry when you did it way back when in high school. We're not going to do that in physical science class. But you do have to know things like what affects how fast these things are going. The concentration affects how fast it is. If you only have one molecule, well, it might react more or less time than if you have a whole slew of molecules. The temperature. Generally, if we want a reaction to happen faster, we can heat it up. Not always, but a lot of times. And also these things called catalysts. And catalysts are pretty cool because catalysts affect a reaction and change how fast the reaction happens, but then you get the catalyst back at the end. It like takes part in only part of the equation. Like it does something and then it does something else, and it gives you the ability to go from one to the other faster.
So, like
A two-part epoxy. Maybe one of those is a catalyst. Yeah, part of the chemical in there is a catalyst. Yeah, but we'll see some examples of catalysts. But it's all about making it easier for the reaction to happen, or well, harder I suppose. But you probably wouldn't have a catalyst to make things harder. Okay. If something is less concentrated, okay, you're going to not bounce molecules together enough inside whatever solution it is to make it happen faster, right? So the more concentrated a sample of nitrogen and oxygen are, the greater likelihood that those two molecules will actually bounce together and, in this case, swap between N2s and O2s to Ns and Os, right? Hey, you know what? I bet now that we learned that stuff from the video, we could say N2 plus O2 yields NO. How many of them?
Just put a 2 on the right hand side.
Yeah, 2 and 2, and we're going to end up with 2, right? Is that a balanced equation? Yeah, there you go. That was easy, right?
That would be good on the test.
That would be good on the test, right? Right. So yeah, so if we had twice as many, yeah. So anyway, that's how. If you have more concentration, you end up with more molecules bouncing together to make this reaction happen. Okay, so that's how concentration can affect reaction rates. Okay, what are you laughing at over there?
No, sir, I just took it out.
All right.
Over here.
Temperature can affect it. If we look at the temperature here, now remember how this reaction rates based on concentration was all about the molecules being more of them, so they bounce together. Well, what happens if they're faster?
Faster reaction.
Yeah, it's going to be a fast reaction, right?
So
And not only that, but if you're too slow, you might not bounce with enough force to actually break those bonds, right? So you've got more reactions because the odds are better they're going to bounce into each other. And second of all, you actually need more energy and be faster to actually have the reaction happen. So some reactions don't happen without enough temperature. I'll give you a very good example, which we talked about in the first question that I flashed up here, and we had talked about it for a minute. The 50 grams of wood. What kind of reaction did we say it was? When you burn things, right? Burning does not happen until you have a high enough temperature, right? At least most substances, right? So for instance, some substances you can burn with a very low temperature, like the stuff on the end of a match, right? When you have the stuff on the end of a match, when you strike it across something, well, that might create some heat, but it also bounces the molecules together and whatever, and that starts the reaction. Anyone know what temperature paper burns at? You should.
Paper?
Yeah, you've all read the book, I'm guessing. Fahrenheit. What's the name of the book? Oh my gosh, you guys don't know this. Fahrenheit 451. You guys have never heard of this book? Oh my gosh, it's a classic book. Okay, there's a book that homework assignment. You have to read this book. It's called Fahrenheit 451. It's by a guy named Ray Bradbury. It was written in the 1950s or 60s. And it's all about these firemen who go and they don't stop fires. They start fires. Like that's the whole job of firemen in this is to burn books. Anyway, I can't believe you don't know that. I'm sad. Fahrenheit 451 is the temperature at which paper burns. That's why he named it the book. Anyway, if your paper isn't that hot, not going to burn. When you get it that hot, it bursts into flames. Okay, it's all about the temperature changing the reaction rate. There won't be a reaction because the molecules of oxygen hitting the paper are not going fast enough until it's all at 451 degrees Fahrenheit.
So now the faster the reaction rate, the more volatile the transfer?
The faster the reaction rate, the more volatile the transfer. I guess you could say that, yeah. I mean,
Like with potassium in the water?
yeah, I mean, if you heat it up, generally, that would probably go faster as well. But that's because, again, there's enough energy and they're bouncing together more frequently. Right? Okay. All right. So now we get into this interesting thing called catalysts. So this is an interesting diagram here. What this is saying is the reaction process is going along like this. The amount of energy you need is going up like this. Okay? Without anything else in the picture here, if you have nitrogen and oxygen, if you have N2 and O2, they need this much energy to turn into nitrogen monoxide, which is NO and NO. Needs that much energy. So that's how you read this graph. Okay? For the reaction to continue here, you need to have that much energy. Okay? In many cases, you don't have that much energy. The N2 and the O2 will just sit there and be happy by themselves. Right? They don't bounce together fast with enough energy to create the other products. Don't worry too much about this graph. But watch what happens when we add a catalyst. Okay? This is another. Oh, I might have missed a picture here. I'm not sure. But in this case, take a look at this. Here we have oxygen 3s, known as ozone. Okay? And that needs this much energy to turn into oxygen 2s. Okay? Normally, like let's say in the upper atmosphere, you don't have ozones bouncing into enough, or bouncing together enough to create oxygen 2s. They stay as ozones because there's not enough energy here to make that change. Okay? And you're stuck with the ozone. If, however, you put some chlorine into the mix, okay? If you take some chlorine, and this is how we write this. We say we have like this, 2O3 with the addition of chlorine gives us 3 O2s. Okay? This chlorine, when you add that to the mix, you actually have a lower boundary. What's happening first is this. The chlorine is doing a subreaction with the O3. And then the chlorine with the oxygens then is doing another reaction, probably with another chlorine, to go back to chlorine gas, but leaves 2 oxygens. So basically, it goes like this. Let's see if I can, I wonder if we can, I don't know if I can figure this out. Basically, it looks like, and it doesn't say it in this one, unfortunately. Basically, it does something like this. I don't want to write the things right now, but let's say you have O3 plus chlorine gas goes to let's see, is it going to be what's that? I don't think it's going to be O2 directly. I think it's going to be like ClO or something like that. Does it? Is this in the book? Ah, good. What is it? Plus what?
Plus O2.
O2. And then what? Does it say the next one?
CIO plus O3.
ClO. So then you go ClO plus
O3.
let me write it down. Let me write it up here so it's not in the thing. ClO plus O3 gives you what?
ClO plus.
What is it? Cl2?
Cl. Plus.
Oh, so this is what happens first.
Yeah.
You got to do it in the right order.
No.
No?
At the bottom there is no 2Cl.
There's what?
On the bottom, on your bottom.
Okay, hold on. I'm going to start here like this. Okay, this is the first equation from the book? Okay. What's the first one?
Cl plus O3.
Okay. Okay. Yields what?
No, you erase your O up there on the left.
All right, hold on. Cl plus O3 gives you what?
ClO plus O2.
ClO plus O2? Okay, and then what? Anything else?
Yeah, that's it for that equation.
That's it.
It doesn't give you anything else?
That's it.
Well, I think what happens now is you end up with CLs again, basically. You end up CL, and anyway, I'll have to look it up. We'll do it next time on the video. You end up with the CL starting at Cl2 and then ending up at Cl2, and you go from O3 to O2 in the middle there. But in the middle, CLs combine with this one, then they uncombine with this one and go back to this. So basically, you start with Cl2 and you end with Cl2. Okay? And you end up going from oxygen 3, which is ozone, to regular old oxygen 2. If you do this in the atmosphere, what happens to the ozone? Goes from ozone to O2. Do you have any more ozone? No. One of the good things about ozone is it keeps bad sun rays from hitting us. Right? It's called the ozone layer, which you've all heard about. The ozone layer is destroyed when you have chlorine in the atmosphere. Well, there's these things called chlorofluorocarbons, which it used to be when you had a aerosol can. It would be made with these chlorofluorocarbons, and when you sprayed it, the little chlorines would release into the atmosphere, go all the way up into the atmosphere, mix with the ozone, turn it into O2, you'd get the chlorines back, and this can go do it to some more ozone, and then do it to some more ozone. I think from something I read, if I recall, one molecule of chlorine, too, can destroy like 200,000 molecules of ozone. Because it's just a catalyst. It doesn't ever actually get destroyed. It gets used, but then recreated at the end. And so that's why the ozone layer gets depleted. Okay? And if you live in Australia, where the ozone layer is the smallest already, it gets depleted the most, you have rules like if you're in school, you have to wear a hat if you're going to go play. They have rules that are like no hat, no play. The kids all have to wear hats when they go outside. It's kind of funny too. They wear the floppy hats like the boonie covers. Yeah. Kind of funny seeing all these like whole classes of kids in their little boonie hats. But anyway, it's because of the ozone layer. It's too bad. But anyway.
How are the schools in Antarctica?
Schools in Antarctica. Yeah, good question. All the penguins. Penguins are getting. Actually, I actually think penguins are getting cancer more because of that. Skin cancer. Yeah. Question. Yeah. No. Oh, okay. All right. So anyway, that's catalysts. Okay. We get the idea that a catalyst is utilized in an equation or a formula, but not used up or not changed. Yeah. In the end.
In regards to when the CLs get pushed up the thing and turns from O3 to O2.
Yeah.
The
When it turns from O3 to O2 and the chlorines go up there,
so
yeah.
the air that's going, it's going from, let's say it's here in Africa, right?
Yeah.
We spray
Yeah.
and goes up there.
Yeah.
It affects just directly above, or is it like it goes up the layer?
Well, it might affect directly above, but then because of the other parts, because of other factors in the atmosphere, you end up with the layer over like Australia and New Zealand being depleted more, and like Antarctica being depleted more because of other factors. But yeah, it might affect it directly above, but then some might fill in, and then it happens all the way down to the bottom.
So South Africa isn't really affected?
I'm not sure. I use Australia because I live there, and I know about that. But otherwise, yeah, I'm not sure where else it's really affected. Okay. All right. So here's a check question. Carefully examine the following reaction sequence of the catalytic formation of ozone. A different one. This is the formation of ozone. O3 from molecular oxygen. Which chemical is the catalyst?
The bottom.
The bottom one?
No.
Well, let's see.
2O+2O2.
You start when you do oxygen with two NOs, nitrogen oxide, and monoxide, I guess, and you end up with nitrogen dioxide. And then you go with nitrogen dioxide becomes nitrogen monoxide again and an oxygen. And then you have one oxygen and some O2s, and you get some O3s. So which one started out the same and ended up the same?
O2, the first one.
Which one? This one?
No.
Nope, you end up with O3s.
Wow.
About NOs. Becomes NO2 and then ends up as nitrogen monoxide again. Right? That one ended up, in the end, it started as nitrogen monoxide. In the process, it became something else, but then it came back and ended up as nitrogen monoxide again. And the oxygen turned from O2 to O3. Okay, so hopefully it's going to be this one. Let's see. Boop, nitrogen monoxide. Okay, so to explain it here, the NO reacts with the O2 to form oxygen with no just plain old elemental oxygen. Reacts with O2 to form O3. In other words, the NO gets this reaction going. As another clue, it's regenerated, which is what we talked about. Okay? All right. All right. Oops, a little thing's missing. Weird. I haven't seen that one before. I don't know why it's missing. Oh well. Energy and chemical reactions. I don't know what that one is. Okay, here's another check question. All right, use the bond energies. This is what that picture showed something about bond energies. Well, we'll walk through it. Use the bond energies below to determine whether the following reaction is exothermic or endothermic. Okay, an exothermic reaction releases energy. Exothermic means it releases energy. Have you ever gone like skiing and you had those little packets, the hand warmers, and you break them, and when you break them, they get really nice and warm, and then you put them in your boot and you lace up your boot, and then it gets so warm that you're like out skiing, you have to like throw your boot off. Anyway, that is an exothermic reaction, meaning the chemicals in there, when you break it, mix together, and they react together such that they create energy.
Is it like a chem light?
Chem light's a good one too, yeah. Yeah. That's actually producing light, which has probably got some heat energy too, yeah, chem light. Okay. Endothermic means the opposite. Have you ever seen the cold packs? You know, the ones when you hurt your knee or whatever? You break the cold pack and it gets nice and cold. That's an endothermic reaction. Okay, endothermic. Okay, well, let's look here. and we're not going to worry too much about the details here, but the hydrogen to hydrogen bond energy is 436. 436 for here. Chlorine is 243. HCl is 431. So if you add 436 and 243 and you end up with just 431, doesn't this have lots of extra energy in there? And you only need 431 for this guy. Turns out that extra energy turned into heat energy. Okay? So it's going to be a lot, actually. So it's an exothermic reaction, and it's a lot, more than 50 kilojoules. Okay? There you go. Okay? You start out with, let's see, 679, and end up with just 431, and you had to release 862.
So it's just like our
Well, it's actually a little different there. Yeah, sorry? It's just like what?
the foods. Yeah, we're in that.
What about it? Oh, yeah, MRE is a good example. Yeah, when you pour that water in there and it gets really hot, that's an exothermic reaction. And it's the chemicals in there mixed with water produce that exothermic reaction. Okay? All right, remember when we talked about entropy a few classes ago? Entropy is tending towards what? Disorder. Okay, if you tend towards disorder, chemical reactions generally tend towards disorder. Okay, it's just kind of the way they are. Okay, when you look at a hot pan radiating heat, that's becoming more disordered because the heat is kind of going into the atmosphere. It's not really the energy is transferring into the oxygen. When gasoline combusts, it makes smaller molecules. The whole point of gasoline is these really long chains of molecules that you burn them, they break into smaller chains, end up going out the back of your tailpipe and creating greenhouse gases. Marbles bouncing on the floor. You take a thing of marbles that are nice and they're very ordered in like a can, and you pour them out and they're all over the place. Disorder, right? We already talked about entropy. The term used to describe the degree to which energy has become dispersed. It's another way of thinking it's more disordered. Reactions that result in an increase in entropy tend to occur on their own. And that's the whole point. They tend to occur on their own. Okay? Exothermic reactions tend to be self-sustaining because they lead to large increases in entropy. In other words, things like fire will keep going and keep burning. And it's very exothermic, right? You don't want to touch a fire because it's hot. That's the whole point. It's releasing all this energy. Okay? And it's self-sustaining because it happens to be leading to products that are smaller and more disordered. This is kind of the way it is. You have to get an endothermic reaction, you generally need more energy added to it. Endothermic reaction, photosynthesis is endothermic, meaning it cools, it actually absorbs energy. Of course it absorbs energy. It's from the sun. That's the whole point of it, right? It's absorbing energy, turning it into the stuff that you can eat in plants, right? Most plants. So photosynthesis continually needs energy, and it's endothermic. Okay? All right. So that's it, actually, for these two chapters. Whew, we made it. Okay, good stuff on chemistry. I think there's only 2 more chemistry chapters, actually. I think. Then we're on to earth science. So forth.